Hello and welcome to this webinar. Good morning, good afternoon, good evening, depending on where you are. My name is Simon Ritter. I'm the Deputy CTO of Azul. What we're going to be talking about in this webinar is what's new in JDK 18. So obviously, as the title suggests, we're going to cover all the new features that have been included in the latest release of Java, which was released, I believe, probably about an hour ago now. Before we get started, a couple of small housekeeping things. The first is that this session will be recorded, is being recorded, and we will send you a link to the recording so that if you want to, you can either watch it again, or if you want to share it with your colleagues or your friends or even your family, then you can do that. If you want slides as well, we'll send you a copy of those. And also, if you have questions as we're going through, please feel free to type those into the GoToWebinar control panel. There is a Q&A section there, and I will address those at the end of the webinar. One other thing that I would like to highlight is that we are doing another webinar next week, same time, same day next week, slightly different subject. We're talking about optimizing runtime performance for cloud native applications. So if you're interested in that, feel free to sign up for that. Now, what I like to do at the beginning of these type of presentations is to ask you, the audience, a question. So if we can bring up the audience poll. We can see that. Yes, great. So the question is, which version of Java are you primarily using in production? And I've given you 5 possible answers here. The first of those is if you're using the sort of older versions of Java. So if you're still on JDK 7 or JDK 6 even, or I know some people even run older versions than that. JDK 8 is the second option, which is one that remains quite popular. Lots of people still on JDK 8. And then JDK 11, which was the previous long-term support release. And now JDK 17 is another possible answer because that's the current long-term support release. And then if you're using something other than that, then there is a something else answer at the end there. So I think we've had a few seconds, and I'm sure that everybody's had a chance to answer that now. So if we could bring up the results, we'll have a quick look at that and see what people have said. Okay, there we go. Oh, interesting. Yes. So I did this presentation this morning in the European time zone, and everybody in the audience was using JDK 11. So I'm interested to see that the breakdown here is that the majority of people were using JDK 8 still, but quite a large number haven't made the switch to JDK 11. It is quite interesting that nobody's got to JDK 17 yet, but then probably you wouldn't expect that because JDK 17 was only 6 months ago, and I know that a lot of people who are looking for long-term support releases, they take time to make that move because of the stability of the release and so on. Okay, so let's move back to the presentation material and start talking about what's new in JDK 18 and so on. First thing to talk about a little bit is the whole idea of how we're seeing Java evolve as a platform. And so I've said here, it's moving Java forward faster. What we've seen is since JDK 9, which was, oh goodness me, way back in, what was it, 2018, 2017, we had the idea that we were going to switch from having feature-driven releases where we potentially had 2, 3, even 4 years between major Java releases to this time-based release model and only 6 months between the versions. And I think it's fair to say that that's working very, very well. We've seen many releases over the last few years, and we've seen a lot of new features being added to the platform in a much quicker way than we ever have before. We've adapted in terms of the specification, we've adapted in terms of delivering the projects and so on. And I think it is fair to say that it's all working very nicely. So this is real kudos to the OpenJDK developers who made this decision to switch this idea. Now, in terms of the way this works, clearly having a new release every 6 months is great for adding new features, but it does make life harder if you're looking for stability in terms of production use. And again, if we look at the results of that quick survey, lots of people are still using JDK 8 because it is actually a long-term support release of Java. People are offering extended support in terms of updates, bug fixes, security patches, and so on. Now, the current long-term support release that we have, JDK 17, I would expect to see quite a few people over the next 6 months to 12 months making a switch. If they're using JDK 11, they will probably move to JDK 17. From the JDK 18 perspective, what we have is what's called a feature release. So this is one that doesn't have extended updates. Even Azul are not offering extended updates to that because we have what we call our medium-term support, and we're not bothering with that with JDK 18. So in terms of the updates that you get for JDK 18, no extended support. There are only 2 scheduled updates, April and July. The way that OpenJDK works is that you have 4 scheduled updates every year, and they're offset from the timing of the release of the new Java versions. What that means is that we're going to get an update to JDK 18 next month, probably won't have a whole lot in it. And then we'll get another one in July, and that will be it. I would suspect that we won't see many people deploying JDK 18 into production. A couple of reasons for that. First is obviously that it is only a feature release, doesn't have extended support. But the other thing is, as we're going to see as we go through the rest of the material, is that there aren't really that many new features that would appeal to developers or even to DevOps or sysadmins in terms of why they would want to make the switch to JDK 18. That is not to say that JDK 18 is in any way a lesser release or a bad release or that kind of thing. It is just the way that the system works in terms of being new features have to be ready to go into release. And in this particular one, there weren't a lot of things that were at that point where they needed to be included. One thing I would most definitely say is keep testing. If you're planning on moving to the next long-term support release after 17, which is going to be JDK 21 in this case, because we're switching from a 3-year release cadence for long-term support to only 2 years, that means that JDK 21 will be the next long-term support release, and that's only 18 months away. So it is important to keep testing against new versions as they come out. Even if you're not going to deploy, have a look, see what's going on, and see if anything could affect your applications so that you're already working on that before the next LTS comes out. Now, I did a sort of survey of JDK 18 by the numbers. First of those is JSR 393, which is the Java specification request, the standard, if you like, for Java SE 18, core Java platform. And it has a JSR which contains 3 specific things. You've got the Java language specification, you've got the Java virtual machine specification, and you've got a definition of the standard class libraries, which must be included in a distribution in order for it to be called Java. Now, in terms of the things that have changed from JDK 17, we have 9 what are called JDK enhancement proposals, or JEPs. And this is the way that most new features are described and proposed for inclusion in the Java platform. So we've got 9 of those, which is actually, I guess it's a slightly small number, but it's not the smallest number we've ever had. We also have 71 new API elements in the class libraries and 3 methods which have been removed. So from a backwards compatibility point of view, that's something to bear in mind. When I looked at those, they really looked like they were pretty obscure APIs, and I don't think very many people, if anybody, will actually be caught out by those. But as I say, keep testing. And they've also removed 2 root certificates as well. Okay, so let's talk about all the individual JEPs that have gone into JDK 18. As I said, there are 9 of those. First of those is the change to using UTF-8 by default. If we look at many of the APIs that are used in Java, if you're accessing textual information, if you're doing file reading, if you're creating network connections, all of those types of things, then there are different overloaded versions of those methods. Some will take a code set which you can specify explicitly in your code to say, I want to use this particular code set, but some will not take a code set, meaning that they will use whatever the default is for the JVM. Now, in the past, the way that this has worked is that the JVM will use whatever the default is on the platform that it's running on. If you're running on Linux, it'll use whatever the default is for Linux. If you're running on Windows, it uses default. If you're running on Mac, it uses default. Great. But what that has led to is that moving between platforms has led to some different behavior. So you might have a code set default on Linux, which is different to on Windows. And then when you move your application, because the default code set is different, the behavior of your application then changes because it's using those code sets. What we want to do in JDK 18 is to bring in this idea of using one code set for the default so that all platforms, if you don't specify one through the API, will use the same code set and therefore have the same behavior. So now UTF-8 is that default code set. If you want to find out, running on an older version, what code set you're using, then you can use this handy little command line here and say Java -x show settings : properties. This actually applies to the really sort of the more modern versions of Java, so you probably wouldn't work on JDK, but it certainly would work on JDK 17 and probably JDK 11. So -x show settings properties -version, and then pipe that through grep file.encoding. Obviously, you've got to have grep on your platform, so that'll work on Linux, great. It'll work on Mac. I'm not sure grep will work on Windows, but anyway, doing that will show you what file encoding you're using. What you might also want to do is to test your applications on an earlier version where you're running your particular code to see if the behavior changes when you move to JDK 18 by having UTF-8 as the default code set. To do that, you can simply add this command line flag -d file.encoding equals UTF-8, and that will change it so that you can test your application. If you find that that does change and you want to revert the behavior on JDK 18 back to the way that it was before, you can use the same command line parameter, but just change it back to whatever you get as a report from the command above. So let's say you're using ISO 8859-1, that's a Western European code set, then you could set that explicitly as the default encoding, -d file.encoding equals ISO 8859-1, and then your application will work in the same way that it did before. So this is one of those things that you look at it initially and you think, oh, okay, that's just like a kind of minor change, but it could potentially have issues in terms of backwards compatibility because of this behavior change in terms of code sets. The second JEP that's been included is the idea of a simple web server. And I have to say, I don't really understand why the OpenJDK developers decided to do this. What they've said is that they will include a very simple web server that only serves up files. So there's no CGI capability, no scripting, no other functionality included. It will just literally enable you to access the files in a given directory through an HTTP connection. Wonderful. Now you can do that using the new JWeb server tool that's included in the JDK. And the way you do that is to run the command in a given directory, and whatever files in that directory and subdirectories will be made available through a web interface. What I've done here is I've run JWeb server -p to say which port I want to have it running on. In this case, I'll use 8080 rather than the default 80. And I also want to bind it to all addresses that I have available on my machine. So I do -b 0000. And then I will see that the messages that come out from the JWeb server says that I'm serving the files in /tump/test and subdirectories, all interfaces, port 8080, the URL that I can access from it. And what I've ended was to go and try downloading a couple of files, and as you can see, it reports back what I've retrieved from there. The reason I find this a little bit confusing is because one of the big things in JDK 9 was the idea of cleaning up the JDK, and they said, the developers said they wanted to remove things that were really sort of superfluous and not core functionality to the JDK itself. And they ended up removing quite a few tools and things that were in there for from sort of historical perspective. So adding the simple web server, I'm not really totally convinced about the benefits of this, but it is there. You can use it. There is also probably, in my opinion, more useful a way of doing this through an API. What you can do here is in your application, if you wanted to make some files available through a web interface, then what you can do is you can say, right, in my code, create a server. We'll use the local variable type inference here. So we don't care what the type of this is. Server is use simple file server dot create file server. We can specify the port that we want through a new iSocket address 8080, specify the path that we want to make files available from, so /tump/test, and then we want verbose output on that as well. And then we just start the server up and we get exactly the same thing. We can access the server through port 8080 and see files in /tump/test. The third feature in terms of JEPs is the inclusion of code snippets in the Java API docs. Java docs has been around right from the very beginning of Java, and it's a great way of enabling you to include the ability to document your API in a way that can then be extracted. So you're writing your code, you include the Java doc style of comments, then you can run Java doc on it, extract out the information, generate some nice Java docs that people can then use if they want to use your API. What we've done here is just to extend that a little bit further. So now we can include code snippets and do it in a way that gets formatted in the way that makes sense for code. I've got an example here. So I've got my Java doc style comment. I say an example of how to use a simple web server, obviously from the previous slide, and we use the @snippet here, and then we can provide all the code that we want in the format with the layout that we want. And as you can see, I can also include a comment here on the output level and say that I want to highlight the substring verbose, just because I want to make it obvious that I'm doing that. And then when the Java doc is generated, we'll see the lower part of the slide here, we get an example of how to use a simple web server. Then we've got formatted code exactly as we've had before, but in this case, verbose is now in bold, it's highlighted. We can see, oh yes, that makes things more obvious to us. So it's a nice kind of addition to the Java docs way of doing things, just allows us to include simple code snippets to help people understand how to use our API. Next JEP is the idea of re-implementing core reflection. Now, reflection has been in Java really from the very beginning. And what it allows us to do is to look at details of the code we're actually using. So we can reflect on things like classes, we can reflect on methods, constructors, fields, and so on. In terms of what this JEP is doing is it's saying, okay, for the methods, method, constructor, and field, they're going to re-implement the way that this actually works underneath to use some of the features that were added in JDK 7, specifically method handles that are part of java.lang.invoke. The rationale behind this is that it will help to reduce the maintenance and development costs of this feature. And I know that for OpenJDK, this is one of the things they have also been looking at, especially since JDK 9, is to see how to make things easier to maintain from the actual core Java perspective. When I looked at this, it's interesting to see that the current implementation uses this JDK internal.reflect.magic accessor implementation. I have to say that I always like things that have magic in them, because you kind of wonder, how does that work? So yes, we've got a magic accessor that's available there. From the point of view of developers, this is totally transparent. There will be no changes in terms of how you will use reflection. All of your code will work in exactly the same way. There are no backwards compatibility issues involved in this. It's just an implementation detail as to how the code works underneath. The other thing that is a reason for implementing things in this way is it's related to Project Valhalla. And that's one of those larger projects moving the Java platform forward. It's the introduction of value types into the Java language and the Java platform. It's also the idea of being able to store primitives in collections without the need to use the wrapper classes. That means that you can have an array list of ints rather than an array list of integers, which you have to generate. If you've got an array of ints, then you have to wrap them in integer objects, create new objects, garbage collect them, and so on. So Project Valhalla is a great idea. We're still a little bit of a way off from that. I don't believe that's coming, certainly not in JDK 19. But this is part of the groundwork that needs to be done to make Project Valhalla a proposition when we finally get to the point that is actually implemented. The Vector API is another JEP that we have, and as I say here, this is not to be confused with the Vector Collection class, which is part of the Collections API introduced way back in 1.2. Now, yes, you can still use Vector if you want to, but nobody really does. Everybody uses the ArrayList class instead because Vector methods are all synchronized and it leads to poor performance. What we're talking about here is nothing to do with that. So the Vector API is all about how you can approach numerically intensive operations in Java and have the hardware take the best possible approach to processing those things. So the idea is that if you look at a modern processor, and even, well, not that modern a processor, there's the concept of vector operations or single instruction, multiple data. If we look at Intel, you've got AVX instructions. These provide a very wide register, 128, 256, even 512 bits wide. And the idea is that you take a sequence of values that you want to process, let's say ints, 32-bit ints, and then you can pack those into that wide register, giving you 4, 8, even 16 integers in one register. And then in a single clock cycle, single machine instruction, you can apply the same operation to all of those elements in the very wide register in one operation. So it's effectively doing them all in parallel. This is great for improving the performance of scalar operations, like I said, numerically intensive operations, array type processing. Now, ideally, we wouldn't need this because what we would hope is that when the JIT compiler looks at a particular method, it will say, right, you're doing some array processing and we've got vector operations available in the processor. Let's take your code, compile it, optimize it, and use those AVX instructions to get the best possible performance. But the issue is that there are lots of situations where the JIT compiler cannot identify the code that you've written as being applicable in terms of applying vector operations to it. Now, just as an example here, I've got 4 values, 10, 14, 11, and 8. What I want to do is add 2 to each of them. If I do that, obviously I can do it sequentially and I can iterate over my array, and each time I can go through an element, I can add 2 to it and generate a result. If I look at the same thing using a vector operation, as I said, we have a very wide register. We can then load that up with 4 values in this case, and when we run a single instruction on that, what will happen is that the hardware will understand that we're not just adding 2 to the whole register, we're adding 2 to each section of the register. So it takes the appropriate action and we get the right results for that. But we're doing 4 in parallel, reducing the amount of time it takes to process our array. Here's a code example. I've got a method which takes 2 arrays. And what I then want to do is to iterate over the first of those arrays and say, if the second array element that matches that is even, I want to add its value to the first array. Okay, that's, might want to do that. The tricky bit here is that because we've got a conditional statement in that, we've got the if b of I ANDed with OX1 equals 0. That's the kind of thing that makes it harder for JIT compilers to figure out that we can use vector operations to process this. If we look at the results of that, if we were to not use vector operations and we simply run that code with hotspot, what we would typically see is something like this. Don't worry about all the individual instructions, but the red boxes indicate that we've got the body of the loop there, and the only optimization that it's actually able to apply is a bit of loop unrolling. It's saying rather than doing one element per iteration of the loop, we know we've got lots of elements, so let's do 2 elements per iteration to reduce the number of iterations and the overhead of doing that. But it doesn't really help us much because we're still doing it sequentially. If we use the vector API, we can explicitly tell the compiler what we want to do. So now what we'll do is we'll look at the same method. The first thing we need is what's called a vector species. And the vector species is our way of identifying what register we're going to use and how we're going to pack that register with values. In this case, the vector species is related to integers because we are going to use an array of ints and process those values. And the species will be a 256-bit wide register. So that means we're using a machine that has AVX2 instructions on it if we're running on Intel. That is a little bit of a limitation because, of course, you as a developer need to understand what hardware you're going to be running on. So you would need to know that you had access to AVX2 versus just AVX. So it's a small thing, but you decide what species you want to use. Having done that, we then have the same piece of code where we iterate over our array of values, but we do it incrementing by the number of the length of the species in terms of the number of ints we can pack in there, which in this case would be 8. So we're jumping by 8 each time. So what we then do is we say, okay, let's go through that and let's take the values and we will then create vectors of those. First thing we need is a mask to indicate where in the vector we're going to pack each element. So, first 32 bits, then the second 32 bits, third 32 bits, and so on. Then what we do is we create vectors from the arrays of the values that we want. So we're taking the values out of the vector A, so the array A, and we're taking the values out of array B, putting those into vectors, and then we say what function we want to perform, which in this case is add B to A if it's valid. Then what we do is we take the values of those out using the mask again and read them back into A so that we've taken them out of the vector register and put them back into the array that we want to process. The net effect of that is that the code that we generate when the JIT compiler runs looks different. So now, rather than just doing that 2 times loop unrolling, now what we're doing is actually using the vector instructions, the AVX2 instructions, filling in the register, doing everything in parallel and getting much better performance from that. Now, the vector API wasn't introduced in JDK 18. It was actually introduced back in JDK 16, but it's now in what's called the 3rd incubator. This is one of those things about the way Java has changed. All of the new things that we add in Java now are either incubator APIs or preview features, meaning that when they're first introduced, they are not set in stone and they're not necessarily part of the standard, which means that we still have the ability to change them based on feedback. It's not beta testing because these are fully formed features, but it does mean we have the ability to change them if we want to. So in this case, they have introduced it as a 3rd incubator, and the 2 changes that they've made since previous releases is firstly to introduce support for the ARM scalable vector extensions. That's great because obviously lots of people are using ARM architectures both on the client side and on the server side. And they've also improved the performance of vector operations that accept certain types of mask on architectures that support masking in hardware. So that's a small change to that. The Internet Address Resolution Service Provider Interface. What this effectively is doing, this is another JEP, is saying that at the moment, the way that if you want to resolve an internet address or a host name is you use whatever the platform's built-in way of doing that is. Now what we're doing is allowing people to say, okay, I don't want to use whichever way the platform does it. I want to provide a different implementation that I can plug in to the JVM to handle this. There are a number of new methods and classes and interfaces which are part of the java.net.spi package. So we've got the inet address resolver, then there's an inner class inet resolver, inet address resolver.lookup policy, inet address resolver provider, and inet address resolver provider configuration. One thing I would say that was interesting to me when I looked at this in a bit more detail was that last one, the configuration, uses a sealed interface. Sealed types and sealed classes were introduced in JDK 15. JDK, we have to remember that, JDK 15, and it's interesting to see them now being used within the standard class libraries. So it was that, like I said, it was interesting to see that that used a sealed interface as the way that it was defined. This is one of those things that really will have no impact on developers, because if you're using internet resolution or address resolution or hostname resolution, that will still work in exactly the same way. It's just if you wanted to support a different way of doing it, then you can now do that. Foreign function and memory API. This is actually part of another larger project, which is called Project Panama. And Project Panama is all about replacing the Java native interface API. JNI has been with us for a long time, and it's always been a bit fiddly to use. I know I've used it for a number of projects, and I always found that the ability to having to do things like create header files, and you've got to create methods, and then you've got to compile stuff, and then you've got to figure out where your standard libraries are, where your native libraries are, and make everything work. It's always been very fiddly. And I remember when I was at Sun Microsystems asking one of the JNI developers about this, and he said, oh yes, that was a deliberate idea. We wanted to make it hard for people to use to discourage them from using it. And you kind of think to yourself, I'm not sure that's the best design approach for an API, is setting out with the idea of making it hard to use. But Panama is all about making it much easier to use. And there are two parts to this. As you would expect, there's the foreign function API and the foreign memory API. Here's an example of using the foreign function API. What we want to do is to make use of a C function outside of the JVM in a library somewhere else. Now, in this case, we're going to use getPID, which is a standard function that's available on Linux, so you can get the process ID. To do that, the first thing we need is a reference to the linker to find where this function is going to be. We can do that through a static method on the CLinker class, so we get the instance, and that will give us the linker. What we then need to do is to figure out where to find the reference to the function that we want. And we do that by figuring out which library to use. Because getPID is part of the underlying operating system, we can use the default library lookup, because that's it's whatever's available to the JVM directly. If we had an external library that we wanted to use, then we could use library lookup and specify an external file that we wanted to use as our library. What we then need to do is to get a reference to, or a handle to, the function that we want. We take our linker and then we say, create me a down call handle for that. We have both down call handles and up call handles. Down call handle is where you're calling from Java to a native function. An up call handler is where you have a callback from native code into your Java code. So what we're doing here is saying to the linker, I want a down call handle, and then I want to look up using the linker the function that I want, which is getPID, and then I need to specify certain things about that in terms of the value that will be returned. And I specify both the type, both in terms of the Java type and also the foreign function type. So in this case, it's a C integer, which maps to a Java integer. And then what I can do is I can simply say, okay, take my getPID, which is my down call handle, invoke that exactly, and that will return an int, which I can print out. Once we get to Project Panama, there will be a JExtract command, and that's going to make life a lot simpler, because what it's going to do is essentially eliminate all of the code which is colored there. So we'll get rid of the linker, we'll get rid of the lookup, we'll get rid of the handle, and we'll simply do a static import or an import on something that's produced by JExtract, and then we can just call it. So the JExtract will do the hard work for us, then we just call whichever function we want. That's going to make life so much easier. Looking at the other side of things from the foreign memory API, what this is about is enabling us to access memory outside of the Java heap. Now, we can already do that to some extent if we look at things like memory mapped files, but what this is doing is saying, how about if I want to allocate some memory outside of the heap to store things which I want to use to communicate with these foreign functions? It's very logical. What I'm doing here is saying, okay, create an array of strings on the heap by creating an array of strings and populating it with mouse, cat, dog, camel. Then what I'm going to do is I'm going to allocate some space in native memory off the heap based on that array of strings. So what I'm doing is saying, create me a memory layout from my string array and allocate enough space to be able to store everything. What I can then do is create a loop, and I can allocate the string off heap and store it using its memory segment. So I could say, okay, here's the allocator that I want to use. I want to allocate enough room for that string based on whichever the string is in terms of that array. And then I'm going to set the value at that index and copy the thing into the off heap memory. So that allows us to do that. It's okay. It's not totally simple, but it's not totally complicated either. As I said, this is again something which is been around in the previous version of Java. So it was introduced in JDK 17. It's now in its second incubator. And in terms of the changes that have been made since JDK 17, there's basically 4 things that are changed. First is that the memory access var handles support more carriers, meaning there are more types that we can use there, for example, Boolean. Also, memory segment, memory address now support more generalized dereferencing, just makes it a little bit easier to use those. And probably the big one for me was the API to obtain the down call method handle is simpler. In the example I showed you on the slide earlier, where we get the reference to the getPid function, that has changed, and it's a lot simpler than it used to be. And then there's also a new API to copy Java arrays to and from memory segments, which is the one that I showed you on the previous slide. Pattern matching for switch, JEP 420. Again, this was a preview feature which was introduced in JDK 17, and it's one that has been continued in JDK 18 with some modifications. If you look at the way that switch works prior to JDK 17, you're quite limited in terms of what types you can switch on. Basically, you can use integral values, an integer, you can use strings, or you can use enumerations. What they did in JDK 17 is to expand that to allow type patterns to be matched. And this is very similar to the type pattern matching for instance of that was included in JDK 14. If we look at an example of that, what I've got here is a method called type tester, which takes something which is an object. And what I want to do is use a switch to figure out what is the specific type of object O. And we can see here that we've got several different cases that are available to us. First of those, which is a new thing for pattern matching for switch, is the idea of matching on a null, because it could be that we want to say, okay, well, if we've got a reference that is null, we need to deal with that rather than throwing a null pointer exception or having to deal with it explicitly before we get to the switch. So we can add a case of null. In that particular situation, we don't have a pattern variable because a null is a null is a null. So there isn't any point in having a variable for it because it doesn't vary. So then we can print out we've got a null type. We can have a specific type of string, and that will have a pattern variable, S, which we can use on the right-hand side of our arrow operator, and we can manipulate that and use it as a string. So we can print out the value of the string. Same with color. We have a pattern variable C. We can dereference that and say, get RGB to get the values of that print those out. We can't match on a primitive because a primitive is not strictly a type in Java, but if we have an array of primitives, that array is a type. So we can have a case of int array and reference that through the pattern variable IA, and we can print out the length on the right-hand side. For anything that doesn't fall into that, we have a default statement that then prints out whatever the thing is to string. In terms of what has changed in the second preview, there are two things which have changed. In terms of the way that the switch works here, is that switches, in the case of pattern matching, have to be exhaustive, which means that we have to cover every possible type that could be passed to that switch statement. That's why in the previous example, we had to have a default case, because if we didn't match on any of the ones above, then we deal with everything else through the default. If we were using a sealed class, then we wouldn't necessarily have to have a default, because we could specify all of the possible things that are involved in that sealed type hierarchy and make sure that we had exhaustive checking on that. So one of the things that they've done in terms of the update to this feature is to have exhaustive checking on switch blocks more precise, specifically with sealed hierarchies. The other thing, they made a small change to what's called dominance checking. And dominance checking is about making sure that when you specify a set of cases which all could possibly match the same thing, that it's the most specific one which gets put first and the least specific one that gets put last. So what I mean by that is, in this example here, what we're doing is we're saying, okay, switch on O, and what we'll do is we'll say, if it's -1 or 1, so very specific to particular values, we'll do something. If it's a case that we have an integer, and remember that -1 and 1 will match on an integer, so those are ones that have, so the dominance is that we have specific values. So we can match on case integer I, have a guarded pattern, so we add the and I is greater than 0, then obviously we're dealing with all positive integer cases, but we've got the dominant pattern above that because 1 is still positive, but that's a very specific one. Now we've got the second one, which means that we're testing against integers that are positive, and then the third one is basically any integer, so 0 or less than 0. So that means that we have the least dominant case at the bottom, most dominant case at the top. And so the compiler will now make sure that you have things in the right order so that you can't mask effectively a case lower down by matching first. So if you put integer I at the top, of course that's going to match first, and you wouldn't then match either the case of -1, 1 or case of integer I and I greater than 0. So that will be rejected by the compiler. The last JEP that we have in JDK 18 is deprecation of finalization for removal. Finalization is a feature in Java that has always been very contentious, and a lot of people don't like it. It has a number of impacts on the way that code works, and the recommendation is not to use it. So the problems you have with finalization are, to start with, around garbage collection. If an object is no longer referenced, but it has a finalizer, you can't immediately garbage collect it because you have to run the finalizer. So rather than garbage collecting it, you put that object onto the finalizer queue and hope that at some point that finalizer queue will get to your object and run the finalizer and then garbage collect it. But of course, there's no guarantee of when that will happen. And if you have very large, complicated objects that have finalizers in them, they could maintain, in effect, references, and you could, even though you're no longer using those objects, you could run out of memory because of the fact that the finalizer is not running. There are other things that affect this. So there's things like unspecified threading. You don't know when the finalizer runs which thread it will run on, and that could potentially have all sorts of issues for you. Similarly, finalization is always enabled, meaning that if there is a finalizer associated with an object, it has to be run, regardless of what that's going to do. Maybe many situations where it doesn't actually need to do any work, but because a finalizer has been declared, it must be put on the finalizer queue and that method must be called. What we've seen more recently is the places where you would typically use finalization are no longer required because many of them can be replaced by try with resources. Now, we do a try, we open a file, do something with it, and then when we exit that try block, we know that the file will be closed or the resource will be closed, so everything is tidied up neatly. So that eliminates the need for finalization in that case. The important thing about this is finalization hasn't been removed yet. So finalization is still there in JDK 18, but still don't use it. And hopefully at some point in the future, it will disappear. There are some new APIs, as I said, 71 to be specific. Many of these, 26, are in the maths APIs. So the math class and the strict math class both get 13 new overloaded versions of ceiling divide, ceiling mod, divide exact, floor divide exact, and unsigned multiply high. So these are all things that provide similar functionality to the existing ceiling function and divide function, or floor function, I should say. So there's different versions of those. Have a look at the documentation and you can see how they work. They're basically just a set of utility functions that people might find useful if they're doing specific mathematical things. Just to summarize then, this is my one marketing slide. Azul, as a company, we provide builds of OpenJDK. One of those is our Zulu builds of OpenJDK, which we provide in all sorts of different versions. We go all the way back to JDK 6, we have JDK 7, JDK 8, lots of people are still using that, JDK 11, 13, 15, 17, 18, and in fact, we even have an early access version of JDK 19. Wide platform support, 64-bit Intel versions for Windows, Mac, and Linux, usual suspects. And if you're using something like Windows XP and you really need to run Java on it in 32-bit mode, we have versions of that for Windows and for Linux. Is a real drop-in replacement for the Oracle JDK, TCK tested, and it's free. So if you want to download it from our website, you can. Just to conclude then, basically, I think the 6-month release cycle, as I've already said, is working very well. Even though JDK 18 is what I would describe as a quiet release, there's lots of interesting things still in there. We've been through all the different bits and pieces. For most developers, they'll probably think, yeah, we'll go with JDK 17 for now, and we'll wait, see what comes with JDK 19. But, as I said, keep testing, check your code, make sure that it works in the way you expect it to. Lots more choices nowadays for OpenJDK distributions. Obviously, ours, Zulu from Azul, it's free. Download it, use it. That's what I would recommend. So with that is the end of the presentation. So I'll say thank you very much. What I'll now do is, as I said, have a look and see if anybody's got any questions. If you do have questions, then please feel free to type those into the GoToWebinar Q&A box. Once again, to reiterate on the housekeeping side of things, we will be sending you a link to the recording of this presentation. We'll also send you a link to the slides. And if you want to join us next week for our webinar, we're doing another one on optimizing runtime performance for cloud native apps. That will be very interesting, well, from my perspective, where we're talking about JIT as a service. So what we call a cloud native compiler. As I said, if anybody does have any questions, because I'm not seeing any at the moment, so I'll give people a sort of few more seconds. If anybody does have a question, then we'll see what there is. Otherwise, we'll think about wrapping up. So, yep, not seeing any questions, in which case I will say thank you very much for listening.